Welcome back. In this video I want to discuss another algorithm called K-Means SMOTE, but I'm also going to take the opportunity to bring all the techniques that we discussed so far together and try to understand why some authors thought that we need yet another adaptation of SMOTE. If we remember from previous lessons, SMOTE is a technique that creates new data by interpolating a new example between one observation chosen at random from the minority class, like this one that we show here, and one of its neighbors. So it looks only at the minority class, it chooses one observation at random, it finds the neighbors, then it chooses one of the neighbors at random, and then it places the new example at a certain distance from the original observation. Some people thought that with SMOTE, we would be creating examples in what are called safe areas. If you can see in this diagram, the separation of the two classes passes around here, so it shouldn't be necessary to create new examples in this area, which is the safe area. We should instead be creating examples that are harder to classify. So we should offer the classification algorithm more observations that are closer to the separation boundary. Therefore, we have these algorithms like borderline SMOTE or SVM SMOTE, and also ADASYN. Now there are other issues of SMOTE itself, and there are those that suggest that SMOTE could generate noise by selecting at random observations that are, for example, surrounded by majority classes. So if, in order to create the new example, we select this observation, we find the nearest neighbors of this observation, and remember that SMOTE only looks at the minority class, we would be creating new examples in this area that is overcrowded by majority class observations, and we don't really want to do that, because most likely this observation is noise, and if it's not noise, it will be really hard to classify correctly. So we should be creating more observations either here or here. And continuing with this diagram, we see that here we have two intra-class clusters, and SMOTE does not contemplate intra-class clusters, because what we ideally want is to create observations in here and in here, but not anywhere in the middle. So the traditional implementation of SMOTE would not contemplate intra-class clusters. Now, how often do we have intra-class clusters? I don't know. It depends on the dataset, and there are many datasets around. The authors of this model quote as an example fraudulent credit card transactions. They say that some transactions that are fraudulent occur in foreign countries. So say if I live in Berlin and a transaction on my credit card is done in Italy, most likely that is a fraudulent transaction. And fraudulent transactions are also high-value transactions, so transactions for high amount. And they say that these are two separate groups that not necessarily occur together. So foreign country transactions do not necessarily need to be high cost to be fraudulent. So they suggest that this is an example where contemplating intra-class creation of new examples would come handy. So the idea of K-Means SMOTE is to boost minority class regions by creating samples within naturally occurring clusters of the minority class. So here we see one prerequisite for implementing this technique. We need to have naturally occurring clusters of the minority class. If our dataset does not have these clusters, then there is no point in using this technique. K-Means SMOTE will contemplate intra-class clusters, and it will avoid introducing noise by creating examples only within those clusters. So K-Means SMOTE has basically three steps. The first step is the clustering step, where we cluster the data utilizing a K-means algorithm. The second step is a filtering step, where we select the clusters that will be oversampled. We wouldn't oversample all the clusters, we will only oversample some of them, those where we have high proportion of minority observations. And I'm going to illustrate this with an example later on. And the third step is to oversample those clusters. And we will create more examples in those clusters that have less observations of the minority class. Here we have a diagram that I took from the article of the creators of this algorithm that shows the 3 steps of K-Means SMOTE. We have a nice dataset that contains minority here and majority observations and 3 naturally occurring clusters, and all of them have observations of both classes. So the first step is to use K-means to identify those clusters, as you see here. Then we determine the imbalance ratio inside each of those clusters. So imbalance ratio is the number of observations from the minority respect to the majority. So here we have 5 crosses to 2 dots. Here we have 1 of the minority class versus 48, and here we have 14 of the minority class versus 1 of the majority. Now we will oversample only clusters where the imbalance ratio is bigger than 1. And this means that by default, we oversample clusters where 50% of the observations are from the minority. And we will oversample more, so we would create more synthetic examples for this cluster, because here we have less observations than here. Here there is a seemingly safe zone because most observations are from the minority. The algorithm is most likely going to get it right. So according to this algorithm, we need to sample or create more examples for this particular cluster. This is how K-Means SMOTE work, and we can go in more details over these steps. So the first step, as I said, is to find the clusters within our data, the naturally occurring clusters. And this we would do with the K-means algorithm utilizing the entire dataset. So as a prerequisite, we need to know K, the number of clusters. And if we don't know it, then we need to treat K as a hyperparameter. So here we are adding some layers of complication. And another thing that we need to consider is that K-means may be slow to converge in huge datasets. So if we have huge datasets, this algorithm may take quite a while to find all the clusters. The second step is the filtering step. How to find the clusters that we want to oversample. By default, we would select those clusters where at least 50% of the observations belong to the minority. That is the same as saying select those with the imbalance ratio of 1, because remember that the imbalance ratio is the number of observations from the minority divided that of the majority. So 50% means that this number and this number are the same, therefore the imbalance ratio of 1. As an alternative, we can increase the imbalance ratio, and therefore we will be selecting clusters with higher proportions of minority class observations. So as you can see, the imbalance ratio quickly becomes another hyperparameter that we need to yet optimize. The third step is the oversampling step, where we determine how many observations to create for each of the clusters. Now, in the previous step, we selected, for example, this cluster and this cluster. Now we need to select how many observations I want to create here and here. And to do that, we're going to assign weights to the clusters, and we will assign higher weights to clusters with less observations from the minority. So to demonstrate how this calculation is done, let's pick this cluster to proceed with the demo. So now just looking at this particular cluster, but the procedure would apply to every cluster individually. The first thing is that we ignore the observations from the majority class. We only look at the observations from the minority. And the first step is to determine the Euclidean distance between all the observations from the minority class in that particular cluster. This is the distance, this is the distance, and this is the distance. In this example, we have 3 distances. Then we determine the mean Euclidean distance, so the mean of these 3 values. And with that, we determine the density. The density is given by the number of observations from the minority class in that cluster divided the mean Euclidean distance at the number of features. This is the formula that the authors have designed. And then we need to calculate the sparsity, which is 1 minus the density. And now we calculate the cluster sparsity, which is the sparsity of this particular cluster divided the sum of the sparsities of all the clusters. So this will automatically return a value between 0 and 1. And now that we know this cluster sparsity, we multiply it by the total number of observations that we want to add to the dataset, and that tells me how many observations I need to create from that particular cluster. And I do this procedure for every single cluster that I decided that I will oversample. The final step is to determine the new examples utilizing traditional SMOTE, so taking one observation from the minority at random within that cluster and extrapolating linearly between one of the neighbors, also from the minority, and also from that particular cluster. There is one thing that we need to consider here is that if the cluster has very few observations, then finding the number of neighbors for the minority class, it might be a problem. We may not have enough neighbors. So again, the number of neighbors becomes another hyperparameter that we need to optimize if we're using K-Means SMOTE. Now I want to wrap up with my thoughts about this technique. K-Means SMOTE is very well thought. It has a logic that makes sense. And the criticisms done to SMOTE, they are true and they are real. The problem that I see is that the implementation of the algorithm, so the implementation of K-Means SMOTE, is not super straightforward because there are some hyperparameters that we need to adjust. For example, the number of clusters of the K-means, the imbalance ratio to filter out the clusters, and then the number of neighbors that we're going to use to create those examples. So there are a lot of variables that we don't know a priori and we need to investigate. And we can treat these as hyperparameters in a hyperparameter optimization procedure, but personally, I would also follow that up with some exploratory data analysis just to make sure that those clusters make sense. So after this lengthy speech about K-Means SMOTE, we can implement it just with 2 lines of code utilizing Imbalanced-learn. We're going to use the K-Means SMOTE class, and the parameters here are the K-Means estimator with the number of clusters that we want and the number of neighbors that we're going to use to interpolate the observations, and also the threshold to filter out the clusters that we want to oversample. With fit-resample, we create the synthetic examples. In the next video, we're going to see this in action with some data. For all of that, I will see you in the next video.